In this video, I'm going to show you how to do a multivariate regression analysis on SPSS. For conducting multivariate regression, you click on Analyze from the top on SPSS, and then you find Regression under the Analyze tab. From Regression, you find Linear, and then we're going to click on that. Once again, you click on Analyze, and then Regression, and then Linear. When you click on this, a window pops up on your screen, and this window wants you to input your dependent variables and your independent variables. I just recorded a video about bivariate regression, so these were the variables I was using for that. Let me start from scratch, and I will input, I'm interested in the relationship between overall satisfaction, quality perceptions overall, and value for money perceptions overall. And so I'm going to put my quality overall variable in the independent variables box, and then value for money variable in the independent variables box as well. So I have two x's. These are my two x's here. And then my y, I want to make the satisfaction, overall satisfaction variable, my dependent variable here. And then I go ahead and click OK. So now I have four boxes that SPSS outputted for me as a result of my regression analysis. The first box here tells me about which ones were my x variables and then which one is my y variable. So I inputted value for money and quality overall as my two different x variables, and then my dependent variable was overall satisfaction. In the second table here, I can see my Pearson's correlation coefficient R, excuse me, and that came out as 0.66. That means that, as you would recall, Pearson's correlation coefficient ranges from -1 to 1. 0.66 is moderate to strong relationship between my x's and my y. So value for money and quality overall is moderately positively related to overall satisfaction. And then I have my r squared variable, which is literally your r squared mathematically, and that came out to be 0.438. This indicates to me that the 40%, 43% of the variability in y can be explained by my x variables. If you actually round it correctly, 44% of the variability in my overall satisfaction, my y variable, can be explained by value for money and quality overall perceptions of customers. And then I have an ANOVA table here that indicates whether the relationship between my x's and y is statistically significantly linear. And my null for this ANOVA is that there is no linear relationship between my variables. So once my f value that comes out of here is statistically significant, if this sig, which is my p-value observed, is smaller than 0.05, then I reject my null, and I can conclude that there is a statistically significant linear relationship between my x's and y's. In this case, there is a statistically significant linear relationship between value for money, quality overall, and overall satisfaction. Now, lastly, I see a coefficients table right here, and let me go ahead and try to visualize that coefficients table for you. All of my coefficients are statistically significant, as you see here in the sig observed p-value column over here. And I I would drop these out of my equation if they were not statistically significant, because as a researcher, I look at the trimmed equation, regression equation, and I usually do not include anything that's not statistically significant. In this case right here, my coefficients are all statistically significant, so I'm going to include them all. So my regression equation is y equals a plus b1 x1 and plus b2 x2 in this case. My y-intercept here is 1.344, statistically significant, plus B, my first slope for quality, is 0.453, statistically significant. And B2, my second slope, is equal to 0.241, again, statistically significant. So this is my regression equation for this regression analysis that SPSS outputted for me. In order to visualize it for you, I am going to draw two different axes here and try to illustrate you the relationship between y and x1 and the relationship between y and x2. A technically more correct way of doing this would be to put it in a 3D dimension with y, x2, and x1 as the axes, and you have to kind of imagine a line that's floating in between all of these three axes. So just to like see it a little more clearly though, I'm gonna try to make it more two graphs that are one-dimensional. So what does your y equal to if your x's are both 0? It equals to 1.3, right? This is the description of a y-intercept. So your y-intercept is 1.3 if your x's are both 0. And as your x1 increases with 1 unit, your y increases by 0.453 units, right? So your slope here for this line is 0.453. So if x equals 1, it's 1.3 plus 0.453, which is somewhere around 1.8. Something like 1.8 is here. And then for 2, it's 1.8 plus 0.453, and then that plus 0.53 for every unit of an increase in your x. So this is the depiction of line y equals 1.344 plus 0.453x1. Similarly, in this one, you're just assuming that x2 is not changing, it's constant. 4, and then so for the second one, let's assume that x1 is constant and draw the relationship between x2 and y. So your y equals again 1.3 if both of your x's are 0. Let's say that x2 is equal to 1 now. Your y will go up 0.241 units, right? For every unit of an increase in x, your y increase is going to be 0.241. So this one has a less steep slope over here. This is a depiction of the line. So this is 1.3 plus 0.241. This is a depiction of the line 1.344 plus 0.241x2. All right, now you also see the standardized coefficients for beta over here that are standardized versions of your B's. And you actually get the R as a result of these coefficients. And the T and the sig indicate whether your coefficients are statistically significant for you. And And in this case, you can just note that standardized beta coefficients are not equal to your R, unlike your in the bivariate regression where these two coefficients are equal to each other, but your Pearson's correlation coefficient of R is calculated using these two variables, the standardized coefficients, beta coefficients here.